All right. Lecture 3, Postulates of Quantum Mechanics, continued. In the previous lecture, we talked about the state space and configuration space and the evolution of the system. And then the last lecture, we kind of left off at the evolution of the simplest evolution of the system, this quantum coin. And initially, my intention was really to go down this rabbit hole and try to get the computations and show them to you. But I decided that I should probably just cover the other postulates and come back to that. And that's what we're going to do in the next lecture. And we'll go through the details of that. And once we have the other postulates, the computations are going to make a little bit more sense, I think. So let's continue through the postulates. So the next one is measurements. And again, I'm drawing comparisons to probability theory. And in probability theory, a measurement really is captured by this idea of a random variable, which is a map from our probability space to the real numbers, has to satisfy some measurable condition, which here we're not going to worry too much about it. We're just kind of are going to think about it in terms of just the map from our state space to the real number. So it's really going to be a measurement. The state space is going to be some random configuration or something, and this random variable is going to return a number, which is going to be your measurement from your experiment or something like that. So this is going to be the idea of these random variables. And here, again, with the specific example of the coin flip, we had that our state space is heads, tails. The set of events, it's all subsets of S. So in here, this notation 2 to the S denotes all the subsets of this set. And in here, this is the set of events, which is all the subsets of S. And here I define the probability function to be heads, to be P for heads. And from this, you can determine that probability of T is equal to 1 minus P, and you can figure out everything else using the rules, the rules for probability or the axioms for the probability function. Typically, random variables, a typical random variable is an indicator function, where it's denoted by this notation. People have different types of notations. I like to do this like bold one with a subset E, where this function is going to return 1 if omega is in the set E, and E is an event, and it's going to return 0 if omega is not in E. So in here, this is just going to be, this I think of an off or on measurement. Are the lights on or off, 1 or 0? Is it hot or cold, yes or no? So I touch it, it's hot, then it's 1. I touch it, it's cold, it's 0, something like this. So this is the basic idea of a measurement, yes or no. And you can actually build more sophisticated measurements or random variables by linear combinations of indicator functions. And in fact, you can there's a precise result that shows that any random variable can be approximated arbitrarily close with a linear combination of indicator functions. So you can build a system of indicator functions that approximate any random variable. So a lot of times in probability theory, it just pays off to think of everything in terms of indicator functions. But in any case, just to show something non-trivial, this x, this random variable, is going to be the difference of the indicator function for heads and tails, and it measures it returns 1 if it's heads and -1 if it's tails. So this is going to tell you whether you get heads or tails. So this random variable is going to determine heads or tails. In here, we can, with a random variable, then in probability you define the statistics, what I call statistics. And typical statistics, these are average properties of your random variables. And this, you have the expected value, which is the average value of the random variable x, which is going to be this average value, that the average between 1 and -1. And the weighted average depends with the probability of being 1 and -1. And then the variance is given this quantity. And then you can continue defining more statistics that kind of like narrow down or give you a precise idea of what your random variable is. So let's do a little quick work. In this case, what's the expected value of x? I guess we got to recall that probability of h is equal to p. That's for you guys to do right now. And let's try to compute the variance of x. Any takers for the expected value? 0. Does everyone agree?
Is it the quantum coin that we talked about?
No, this is just the classical coin. Benjamin?
I go with 2p minus 1.
2p minus 1. So we have two possible solutions.
It's 0 for a fair coin.
Yeah.
I changed my.
All right. We change it. All right. Yeah. If p equals 1/2. Yeah. So. And actually, I'm gonna denote 1 minus p. Typically, we denote it by q. So this could also be. I like to denote it with p minus q. How about for the variance? So for the variance, we already computed this part. We just need to square p minus q. Squared. And now we just need the expected value of x squared. And x can only take two values, 1 and -1. So x squared can only take what values? 1. So the expected value of x squared is 1, because it's the average value of x squared, and x squared is always equal to 1. So in this case, it's equal to 1, which I'm just going to write p plus q squared. And this is just going to give me 4pq. So just so that we're on the same page, and these are the type of things that we want to compute. And spoiler alert, these are the type of things that we also want to compute with the quantum coin. And just for consistency, we have this quantities. in the quantum case, measurements are a little bit more tricky. Even so, in here, it pays off, or initially, you should just think of measurements from a more pragmatic point of view. There's a lot of confusion in measurements in the quantum case, especially because sometimes people expect the act of a measurement to be some type of dynamical evolution that should be described by a unitary operator, as we described it in the previous lecture, but somehow that is not consistent with things, and somehow it's an interaction of the quantum world and the classical world, and it's kind of wraps your head into a pretzel. So we just kind of take this axiomatically that these are measurements, and measurements are going to be given by a collection of measurement operators. And it's just going to be some matrices that you can think of them that are indexed by M, which are going to be some measurement index, which describes the outcome of your measurement. And in particular, you require this condition that the measurements, if you take the measurement times its conjugate transpose and add over all the measurements, then you get the identity. So you have a collection of measurements. And the way that it looks, for instance, in this quantum coin case, where we have heads or tails, we can have the measurement, what we're interested is in measuring heads or tails. We have an operator to measure heads, and we have an operator, oh no, wait, that was right. We have an operator to measure heads and an operator to measure tails. And then you take the conjugate transpose, which is like you transpose it and you take the conjugate, and here everything's real, so it's just the conjugation, and you can easily check that this are a complete system. So this is a complete system of measurements, or completeness. This condition is completeness. So you can check that these two measurement heads or tails are complete. And just to go a bit further, if we assume we have a state that's in a superposition of heads and tails with weight alpha and beta, and you can think of this as a column vector alpha beta, then you'll note that if you take this quantity, recall that this is just this, and you take this dot product, then you obtain that this quantity is going to give you alpha squared. And this is the interpretation that the probability of measuring M, in this case, would be probability of measuring heads is going to be given by this quantity, by this measurement. And this is the interpretation in general. This is where probability actually comes into quantum mechanics, by this interpretation of measurements, that whenever you're measuring things, you obtain them up to a certain probability. Benjamin.
Looks like one of those vectors didn't get one of the entries knocked out, because that would...
Oh, yeah. You're right. So in here, what I'm doing here first is I multiply this times this, and this should lead to this. Nice catch. And then we get alpha squared. Modulus alpha squared. And this is where the probability starts coming in. It says that if you measure with this heads measurement, then the probability that you obtain a heads measurement is going to be given by alpha squared. And if you were to do the same thing with the tails operator measurement, then the probability of obtaining tails measurement would be beta squared. And the fact that we have a complete system implies that the total probability adds up to 1. Still, I think there's a subtle thing to remark is that this state psi is not that we have lack of information which leads to a probability. It's not like we flipped a coin, it landed, and we put a box or like we put our hand over it. It's not that the system has landed and we just don't know the information, which leads to a probability. That's the classical case of what probability is happening. That was the classical case. In this case, it's really a superposition of H and T, heads and tails, that both things could happen and they happen with certain probability. So in the quantum case, it's more like, bless you. Did you sneeze? All right, good. I really think it's bless you. I think yeah. I'm sorry. You're not blessed. I think it's the responsibility of the speaker to actually bless the people, because anyone else that's not speaking is rude to interrupt the speaker, so it's really falls on the speaker not to make other people rude because they're trying to be polite. So I'm very particular about sneezes. Anyway, and I get distracted easily. So the analogy was that in the classical probabilistic case, you flip a coin, it lands, you put your hand over it. Actually, I'll do it like this now, like this. And you don't know, you lack information, so you have some probability. It's either heads or tails. But in the quantum case, you flip a coin, and it's more like the coin hasn't landed. That it's in a superposition in both in both heads and tails. So it's more like it's still up in the air. So that it's not that we lack information, is that the coin is still mid-flip, and and it hasn't landed. But once you make a measurement, that corresponds to the coin actually landing and it being either heads or tails. And then the fact that you're making a measurement, and that means that the coin has landed, that actually is going to collapse the wave function. And this is the phrase that you'll see often in quantum mechanics, that once you make a measurement, it's going to determine the state of the system, and it's going to collapse the wave function to that specific outcome of the measurement. And in this case, for instance, this is what happens. Once we have psi and we measure it, then the state evolves according to this rule, where you apply the measurement. So you've measured the state, and then you have to normalize it so that the norm of the state is equal to 1. So this is a normalization factor down here. And you have collapsed it to a specific measurement, m. And once you've done the measurement, and in the quantum coin, this corresponds to the following, where you apply this operator here, and you normalize it, and then you obtain this, which is just the heads. You've collapsed your wave function to heads with this coefficient in front of it. This is norm 1, but it might have a face that's not necessarily equal to 1. So this is a number with absolute value equal to 1, so that the probability then is equal to 1. Questions? Mm-hmm.
M sub m is not like the entire measurement, like it's just the head.
Mm-hmm. Yeah, this is to a specific measurement if you apply one specific measurement. And then additionally, in theory, the measurements could be any linear operators, but in the case where the measurements are actually orthogonal operators, meaning that if you compose two measurements, then it's the same as the first one if they're the same measurement, or it's equal to 0 if they're different measurements. And we have that the measurements are Hermitian, that they satisfy this property, then we can define an observable operator that takes into account all the different outcomes and multiplies it times the value corresponding to that outcome. And in that case, we have that the statistics, you can define them as follows, where the expected value of these measurements, which in physics notation is noted this way, is going to be given by this quantity. And the variance is you just do the same type of formula where you have expected value of m squared minus expected value of m squared. So let's try and do this computation again. And for the case of the quantum coin, you can check that the operators are going to be orthogonal and projections. And to the heads operator, I associate a 1 for my outcome, and for the tails operator, I associate a -1, and I want to compute the expected value. And in here, we're still working with psi is equal to alpha beta. So what's the expected value in this case? I'll give you a minute to work on it. Any takers? Yeah, Derek?
Got alpha squared minus beta squared.
How about everyone else? Yeah. And in here, you can think of alpha squared as P and beta squared as Q in the classical system. So it gives us the same P minus Q expected value. So it matches that. Just for sake of time, I'm going to skip the computation for the variance, but for the variance, you want to compute, or maybe I'll just do it real quick. So in here, we have alpha squared minus beta squared. And for the variance, we want to do m squared minus m squared, and this is going to be m squared is equal to 1, 1, 0, 0, 1, and then minus alpha squared minus beta squared squared. And that's the identity. M squared is the identity operator, so that's just going to be 1, which I'm just going to write as alpha squared plus beta squared, and then squared minus alpha squared minus beta squared squared, and then I get 4 alpha squared beta squared, which again, this is kind of like P minus Q, and this is 4PQ. If you do identify alpha squared with P and beta squared with Q. Questions? All right, so now let me wrap up this part with compositions. In the probability case, in the compositions of two systems, you're going to have two probability spaces, S1 beta B1 P1 and S2 B2 P2. And when you create a composition, there's rules to just create a composition of both systems. For the state space, you just take the Cartesian product of the sets, S1 and S2. For the events, for all the possible events, you have to take a more involved product, but in particular, if B1 and B2 are just all the subsets of S1 and S2, then it's just going to be all the subsets of S1 and S2. And then the probability function is going to be determined by the by base times height, essentially. So if you essentially what you do is, in general, you would do, you have this S1 space, S2 space, and then you want to compute the probability of some event E. And what you do is you create a grid, a really fine grid, and for each rectangle, you compute the probability as base times height. And the probability of the base is going to be given by P1, and the probability of the height is going to be given by P2. And then by creating a small enough grid, you can then compute the probability of the whole thing using this rule. And so this is how you would create a composition of two systems. And in here, for the two coin flips, we can create a composition of two coin flips where S1 and S2 are both heads tails. The sets of events are just all the subset of each SI. Then the composition is just going to be the Cartesian product of S1 and S2. It's going to be heads, 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 tails, tails, heads, tails, tails. And the set of events is just going to be all subsets of S1, S2. Again, in all these cases that I'm looking at the finite sets, then we can just B1 and B2 are always just going to be trivial, and they're just going to be all subsets of the outcome space. And in here, the probability of a specific outcome is just going to be P times the number of heads times Q to the number of tails. And you can do you can then, for instance, in here, the outcome space, you can think of it as heads, tails, and tails, heads, and tails, tails. And if you do probability of at least one head, then this really is this region, at least one head. And the way that you compute this probability is that you break it into a grid. and you compute the probability of each square on its own, where you can do base times height. So the probability of this one is going to be PQ, P squared, and PQ. So each one of those squares, you can just do the formula base times height. You can't do base times height on this whole thing. It's not going to give you the right thing, so you just break it up into small rectangles, and then you add it up, and then you would get P squared plus 2PQ. Anyway, so that's in the classical case. In the quantum case, your two systems are going to be given by two Hilbert spaces, H1 and H2, and the composition is going to be given by tensor product, H1 and H2, tensor product of H1 and H2. And really what this means is that if VI is an orthonormal basis of H1 and Wj is an orthonormal basis of H2, then you can create an orthonormal basis of H1 and H2, and it's going to be given by pairs Vi Wj, which is often denoted this way too, with the tensor product. And in here, I need two things to define a Hilbert space. One thing is a vector space. The second thing is an inner product, yes. And have I given you the definition of the inner product in this description? Joseph says no. Johannes says no. Can anyone see the definition of the inner product? Benjamin?
Handle each space separately.
Almost. Getting warmer. I claim that it's there. It's just not explicit. And in here, it's there because I've told you that this is an orthonormal basis. And being an orthonormal basis, that means that these vectors are orthogonal to each other. So when you take the dot product of these vectors, if they're different, it's going to be 0. If they're the same, it's going to be 1. And really, since they're also a basis, then you can do any vector you can write as a linear combination of these guys, and then you can do the dot product by linearity. So that's how you would do it. And for instance, if you had, for instance, in the quantum coin, actually I'll do it in the next one. In this example, so in the quantum coin, two quantum coins, we have H1 and H2 are going to be heads, tails, and they're C2. And if I take the tensor product of H1 and H2, I'm going to have that the elements, so this is my orthonormal basis for H1 and H2, and my orthonormal basis for the tensor product is going to be HH, HT, TH, and TT. So this is going to be my orthonormal basis, and the fact that it's a basis is that any element in the tensor product can be written down as a linear combination of these basis elements. So quick question, what's the dimension of this? So this is going to be C2 tensor C2. What's the dimension of this space? 4, yeah. So this is, you can actually think of this as C4. And then going back to the dot product in this case, you have that, for instance, that HH and HT, since they're orthogonal, this is going to be 0. And in particular, if you were to do something like HH 1/2 plus HT 1/3, and you did the dot product with ht plus 2tt. By linearity, you try to do the dot product of this with this and this. These are all 0. And then you do the dot product of this with this. This is going to be 1. And then the dot product with this and this. This is going to be 0. And this is going to give you 1/3. Does that make sense? How I got 1/3? Linearity and orthonormal. So in here, I've really given you a definition of a Hilbert space by describing what the basis would be. If you take one basis of one and the other, and then you can compose them to create a basis of the other ones. So, and this is basically it for the postulates of quantum mechanics. In the next lecture, I want to actually look at the evolution of a system, of the simplest system, because because as systems get more complicated, it's not trivial to actually figure out the evolution, and I just want to make sure we know how to handle the simplest case. And in particular, to actually determine the evolution of a system, you need to take the exponential of a matrix. And to take the exponential of a matrix, it suffices to diagonalize the matrix. That's easier said than done. Diagonalizing a matrix is hard business. You can make a career diagonalizing matrices. That's actually how I make my living, diagonalizing a matrix, an arbitrarily large matrix. That was my part of my thesis project. And so in practice it's difficult, but in theory, if you can diagonalize the matrix, then you could take the exponential. And in particular, if you have a matrix M with this type of diagonalization, so this is going to be your Hermitian your matrix M, and you can write it in this format: A inverse a diagonal matrix A, where, wow, this one almost got away. Where, no, this is lambda. This is lambda. Then the exponential of the matrix is just going to be A e to the lambdas, A inverse. So you really just exponentiate the thing in the middle. And these are going to be zeros, everything else. So this is how you can diagonalize a matrix, and we needed to actually compute the dynamics of our quantum systems. And here I have a short proof of this fact of taking the exponential of the matrix. I'm not going to go too much into it, but by definition, you define the exponential of the matrix to be this series expansion, where you take the kth power of m and divide by k factorial. So taking k powers of matrices we know how to do, and we can take infinite sums. And in here, for m, you take this substitution, and you write it this way. And you can actually check that this is equal to this by just doing an expansion of this term. And you can see that as you multiply terms like this, A inverse and A are going to cancel if they're consecutively stacked. So the A's in the middle are going to disappear, and you can just factor them out, A and A inverse, out of the whole thing. This is the definition of the exponential, and you can check that this is e to the lambdas. So you can actually compute it. And in here, the idea is that we just need to, in what we'll do in the next lecture, we'll actually just, we'll do it for a 2x2 system and try to do the exponential of the matrix. And for Hermitian matrices, which satisfy this property, there's some additional properties that will help us compute the diagonalization or the exponential of the matrix. Three properties. The first two are that the eigenvalues of a Hermitian matrix are real. The second one is that the eigenvectors are orthogonal if they have different eigenvalues. So in most cases, I assume that all the eigenvalues are different, are distinct. If not, then it's something else. And then using these first two properties, we can figure out the diagonalization of the matrix. And in particular, what the two properties will do for us is that they're gonna give us the inverse of A, because part of the difficulty here, it's not only finding the eigenvectors. So to diagonalize, you need to find eigenvectors, and then you would need to take the inverse of a matrix. And taking the inverse of a matrix is difficult in general, but if we have these two properties, we can actually find the inverse of a matrix pretty straightforward. So in the next lecture, I'll start by giving a quick proof of these properties, and then we'll spend some time with a specific system where I'll break you up into group work, and you'll take the exponential of the matrix and do the probability and do the interpretation, and then we'll come back together as a class and discuss the classical limit. And that's it for now. Any questions?
Quick one.
Yeah,
So,
Prince.
Since H is Hermitian, not H, will A have to be unitary? Or not necessarily?
Not necessarily.
Okay.
Yeah. Good question.